So today we are gonna do a tutorial on the beam problem, plane beam problem, and so most of the steps are the same as truss, and but for the difference, first we need to know the difference of the truss and beam. So what is the difference of truss and beam problem? What is the difference of truss and beam?
Non-axial forces.
And?
Moments on the,
yeah.
on the beam.
Yeah. So truss is subject to the axial force and only has sigma xx, right? But the beam is subject to the bending problem, and so it can has a bending moment, and also for the truss problem, it only has translational degree freedom. If it's 2D problem, only translational degree freedom in x direction and y direction. But for beam problem, we have rotational degree freedom x around the z-axis. So we have 3 degree freedom for the 2D beam. So for 2D beam, we have translation degree freedom in the x direction, y direction, and rotational degree freedom about the z-axis. And if it's 3D, we have 6 degree freedom. So it either translational degree freedom in x, y, z, or a rotational degree freedom about 3 axes. So this is the main difference of truss and beam. And also in truss problem, because we only have the axial force, so the result probably we need to know is elongation and sigma xx, right? But for beam problem, once we have bending, we have the bending moment result and the deflection, the displacement in y direction, and also the sigma xx is kind of different. So when we calculate the truss problem for the truss, when we calculate the sigma xx, is f over a, right? And if it's elongation, so as I said last time, for beam problem, as long as I know the cross-section area, I can calculate the sigma xx and elongation. But for beam problem, the sigma xx is my over I, and this deflection is it depends on your loading condition and boundary condition. So it should have a moment inertia here, and here you have a function of x. So if the loading condition is a bending moment, it should be, this deflection should be a function of x, right? It should be a function, you should have a, yeah, quadratic here. And so if it's a concentrated force, this deflection should be a function of x cubic.
What is the symbol you're using for deflection? Is it a V?
V.
Okay.
Or you can add, because normally in FEA we use U as a displacement in x direction and V as a displacement in y direction. So this V is a deflection, the displacement in y direction. And if the loading condition is a distributed force, constant distributed force, this deflection should be 4th order, right? This is the background knowledge from your mechanics materials, not from FEA. It's just a review. So if this distributed force change linearly, this deflection should be a function of x 5th order. So the first problem is that I here, for beam problem, even if we have the same cross-section area, if the geometry is different, the sigma xx will be different. For example, this shape and this shape. If these two had the same A, but for truss problem, if this is cross section geometry for truss, the result will be the same. But for the beam problem, these two have same A, but I will be different, right? So this stress and deflection will have different results. And even if we have the same geometry, but if I bend it in different direction, for example, for this kind of rectangular shape, if I bend in this way or this way, this I will be different. So the result will be different. So in the definition, Abaqus definition part, we need to be very careful. What is the geometry? What is length in this direction? What is length in this direction? And also, how to orient your geometry, your beam problem. And also, another problem is that for this part, later we will see that for beam problem, we use a cubic polynomial for the interpolation. So what we do is that we calculate everything at the integration point or the node, and then in between we use a cubic polynomial to do this interpolation. So this means that if the beam is subject to bending moment or concentrated force, one element will give you accurate result, right? Because this is like second order and cubic. But if it has the constant distributed force or linear change distributed force, this beam element can only approximate. Do you know what I mean? This cubic polynomial cannot represent the accurate change of this fourth order and fifth order, so it can only approximate. So it means that in our beam problem, if your beam problem only subject to concentrated force or pure bending moment, you can just use one element and it can give you accurate result. But if your beam problem is subject to the distributed force, constant or linear change, or even more complicated loading condition, you should use more elements. And the situation here is that the more elements you use, the more accurate result you will have, because it can only approximate. So this is the difference here. And so we will see that later. I will do a simple beam problem on Abaqus, and I will explain the difference, how you define the section, how you define the beam orientation, how you do the different seating, and also check the result. Because last time we only checked the result of displacement and also the sigma axis, and now this time we need to check the result of bending moment and also shear force. Probably we will not use shear force here. So this is the basic problem here, and I don't think I will use this one as an example. I can explain. I will use a more complicated problem as example, but for this problem you can just do it after class, and you can follow this slide, do it step by step. And for this problem is that there's one beam or two beams, doesn't matter, and it subject to a line force here. You say constantly distributed force, and the boundary condition on both sides are clamped, and the length, also the circular section geometry, cross section geometry are given. So you can try this problem after class yourself, and if there's any problem, you can contact me. But the question I will do today is I will write it here. So here is a clamped boundary condition here. Boundary condition here is clamped, and I have a concentrated force in the x direction, 1000 Newton, and I have a pressure on the upper surface, constant. Pascal. Loading condition, boundary condition, and material property, Young's modulus 100 megapascal. Poisson ratio 0.3. What else do we need? The cross section of this, the cross section geometry of this one is I use rectangular shape, and dimension in this one is 10 millimeter, and dimension in of this 20 millimeter. So this is for example, if we see it from this side, it should be look like this. And what else do we need? Boundary condition, loading condition, material property, cross-section geometry. Okay, I think I can do it on Abaqus now.
So all three have the same cross-sectional area?
Yeah, yeah. This is too slow. Okay. So for the part that is that are same as last time, I will do it very quickly. And if you feel confused or anything, you can stop me and ask me question. Part same as last time, 2D planar deformable wire, and because the dimension of this truss are 1 meter, 2 meter, 1 meter, I forgot. The length of this is 1 meter, 2 meter here, 1 meter here. So I can use 5 here, it doesn't matter, general size. So I add dimension. This as 1, and add dimension. This as 2.
Is there like a you just left clicking on each node, and then it'll automatically pull out the dimension like that, or are you hitting another key while you're clicking?
I didn't hit any key. Just use this one.
Mm-hmm.
Yeah. You mean add dimension?
Yeah, to add the dimension.
No, you just click this one and click this one, then it automatically add dimension.
Okay.
Yeah. So the geometry is done, very simple. 1 meter, 2 meter, and 1 meter. Now let's see the material property. Same as last time, mechanical, elasticity, elastic, and Young's modulus 1E8, Poisson ratio 0.3. Section. So last time we used truss, right? So this time we use beam. So we can see the difference here that now we need to, last time we only defined the cross-section area, right? The only information we gave. This time we need to, you see here, create beam profile. So it's what's the shape of your cross-section geometry. There's a lot of options: box, pipe, circular, rectangular, and yeah, you can also define your own arbitrary or generalized more complicated situation. But today we'll use the rectangular here. For the example in the slides, it's a circular, so you can try it after class.
What is a box? What's the difference between a box and rectangular?
You can see it if you want to try. So this is box.
Okay.
Yeah. Rectangular. So as I said, for this problem, if I see from this side, it should look like this. So we need to be very careful that how to define this direction. So first, you can see that here, it asks you the direction 1 and direction 2. And in the later beam orientation assignment, it will ask you how will you orient this 1 direction and 2 direction. So what we do is that we define this as 1 direction and this as 2 direction. This is 20 millimeter and this 10 millimeter. And then later when we define this beam orientation, we define this one as into the screen, and this direction as the in the y-axis. So you know what I mean. So we define this as 1, this as 2, and when we assign the beam orientation, we assign this is into the beam direction, and this is upward direction. So we'll check it later. So the A should be 20 millimeter, right? Remember to make it the unit consistent. B should be 10 millimeter. So this is the difference of the beam problem and the truss problem, and the rest of it, don't change it. Okay, and now let's do the assignment. Assign section. Select region to be assigned a section. I select whole region. The section 1 I just defined. And one more step, compared to truss problem, we need to assign beam section orientation. So select region to be assigned the beam orientation, I select whole region, because the whole structure will orient, the beam problem will orient in the same way. So we can see that there's a red arrow direction. This is called tangent direction. So this direction is defined by how you sketch this geometry, because I sketch from here, start from here to here to here to here, right? So it's like from your starting point to end point. This direction, when I start from here to here, this direction is called tangent direction. And the N1 direction, as I said, the one direction I want to define into the screen. So this, you can see 0, 0, -1 means into the screen direction, right? This is default setting. I don't need to change it. And then you can see that tangent direction is in this direction, and this dot means into the screen direction. And the we cross product this tangent direction and N1 direction is N2 direction. We confirm. So if you still get confused, you can go back to the slide, and there is some explanation here. Okay, I need this slide. So we can either define tangent direction as this direction or this direction, it doesn't matter. But the cross product of the T direction and N1 direction should be N2 direction. And N1 direction and N2 direction is the direction of the 1 and 2 I just defined there. So can see from here, this is T direction. This is determined by how you sketch your geometry. You can change it. And N1 direction is into screen direction. That's why default is say that 0, 0, -1. And this, when you define this T direction and N1 direction, N2 direction is determined. Is this clear? Okay. So.
Can I ask a question?
Yeah.
When so like after you go beam selection orientation, and then you go and select the whole region, and it allows you to like put in the coordinates at the bottom. The default is setting the direction for N1.
Yeah.
And then knowing your N1 and knowing your tangent direction,
yeah,
it defines the whole thing.
Yeah.
Okay.
So the T direction, tangent direction is from when you sketch it from the starting node and ending node, that is determined. And N1 direction is by default is 0, 0, -1. Of course, you can change it if you want. And the cross product of T direction and N1 direction is N2 direction. So you do not need to define the N2 direction as long as you determine the T and N1. So if you want to make sure that your beam is oriented in the way you want, you can actually check it on the Abaqus. So you can go to View and Part Display option, and you can see here render beam profiles. Right now it just uses line, but if you want to see how this beam oriented, you can use render beam profiles and add a scale factor 5 to magnify this cross section so you can see it more clearly. Let's rotate. So it is the way we want, right? As I said, I want to So if I look in this direction, I want to orient it like in this way. So this is correct, right? So you can check on your Abaqus if you do this step.
Right now, since you haven't done anything to the nodes, does it treat it as one continuous beam or 3 separate pieces?
3 beams. 3 beams. So some students asked me the question that when they rotate this beam, it's hard for them to rotate it back in the original position. So what we can do is that, because for this beam, if I define this x-axis, this y-axis, and into the screen and z-axis, we are basically looking at the z-axis, right? So what we can do is that I click here, this little z here. So it's back. If somehow you cannot rotate back. And let's remove this render beam profile.
Can you repeat that last step? How to get it back, the orientation?
Here, for example, if I want to see it from the x-axis, or I want to see it from the y-axis, or z-axis. Okay. Any question here? So let me remove this one. So sketch the geometry, material property section. Now let's go to assembly. Assembly is same as last time. Create instance, and you can either use mesh on part, mesh on instance, because it's only one part, one instance, doesn't matter. And then create steps. Same as last time. Linear perturbation, static linear perturbation. But the difference is that for the field output request, last time, as I said, Abaqus generate CF concentrated force, LE logarithmic strain, RF reaction force, S strain, and U displacement. This default setting for truss problem is good enough, but for our beam problem, we probably need to know the bending moment, right? So we need to add one more term here, section force. So in the field output result, we can know the bending moment result. Otherwise, there's no way you can check the bending moment results. So remember to add one more output request here, section force and the moment SF. Question?
What was just to go back? What is the purpose of setting the steps?
So for Abaqus, you can have a lot of different results. You see here, you can generate different results. But most of the time, we don't need to have all the results in your output database because it's like too much and it's not necessary. So Abaqus allow you to manage this, what the result you want in your field output report. So the default setting that it will only generate strain, reaction force, displacement, everything, but there's no section force, section moment. Section force means shear force in the beam problem. Section moment means beam bending results, bending moment result. So you need to add this one. So in the output result, in the report, you can have the bending moment results. Clear?
Yeah, I wasn't saying for the output. I was just saying when you set when you're setting the steps, what is the point of setting? Like, what is the first step, and then what is the linear perturbation?
So you have to set a step because you normally we put the boundary condition in the initial step and the loading condition in the step 1. And in the future, if you have the very complicated project, probably you have like step 1, I add the horizontal force, and step 2, I add vertical force, and then yeah, create as many steps as you want. That is the purpose of steps.
Okay.
Yeah.
And it's just so that Abaqus can walk through it step by step when it's.
Yeah. So did I add it? Okay. Add it. So the steps mean that for anything you apply the initial step, for example, the boundary condition, it means that in the whole analysis, the boundary condition keeps the same. This boundary condition is applied for the whole analysis, doesn't change. But for step 1, step 2, step 3, you can do some like, I will only run step 1, and then only run step 2, or like a continuous, like step 1 first and step 2, and then see how it happens. So you can manage how to do it. But for the something like boundary condition, I don't want any boundary change in the whole analysis. I just put it in the initial step. So this is step and field output request. And now we can do a boundary condition. As I said, change this to initial. And we can either use symmetry, anti-symmetry, encaster, or displacement rotation. So I will use, it's the same boundary condition on 2 nodes, but I will use different ones so you can see how to use them. Both of them are clamped. So I will select this one first. Encaster means clamped. So all degree freedom are fixed. Even though we only have this problem is a 2D problem, we only have U1, U2, and UR3, right? But yeah, this is the same. So another way is that for the other node, I can use displacement rotation, and I select this one. So you see 2D problem only has U1, U2, UR3. So translational degree freedom in X direction, in Y direction, and rotational degree freedom about the axis. So these two are the same, just different way to define it. And then the loads. Apply loading condition, change this to step 1. We have 2 loading conditions. One is concentrate the force. It concentrate the force at this node. And CF1 concentrate force in X direction is 10,000. No, 1,000. And then apply another nodes. Now this time I use pressure. Select surface for the load. So I select this surface. And you can see that select side for the edges, either the upper side or magenta or the lower side yellow. So this means that if I select this side, the pressure is applied on the upper surface, and because pressure is by default, it's like applied towards this surface, so it's like downward. And if I select this yellow, means the upward. So I want it applied on the upper surface, and so magnitude is 300. So this is the concentrated force and pressure. And be careful when you do your when you try to do the example on the slide. It is a little bit different. So you can see here. It is also distributed force, but this distributed force is given as a. Oh, sorry. What's the difference here?
Per length instead of per unit area?
Yeah, so the unit is different. This is line force. So when we apply this line force, we can use pressure, but you need to like convert this to the Newton per meter or Newton per meter square. So for this line force, what we can do is that this line node and continue. For example, I want to apply it here. And you can component 1 is in X direction, component 2 in Y direction. And also, if it's positive value, is in positive X direction, negative value in negative direction. So this is how you, when you do the example problem in the slides. Any question here?
So what's the default, I guess, restrictions on the nodes? Like, did it constrain the upper 2 nodes?
The upper 2 nodes? They will have it means that the node on this bin and node on this bin will have the same displacement, and they can.
Can they hinge about each other?
No. So for bin problem, for the truss problem, because truss doesn't have rotational degree freedom, so if you have a node on the truss, there's no way you can control this rotation. That's why in the truss problem, we cannot use like many elements on one truss. You can only use one element one truss. But because we have rotational degree freedom, so somehow you can have a way, being element type, this element type is designed in a way that it can somehow control this rotation. So it will not collapse, don't worry about that. So boundary condition, loading condition are done. We can now let's go to mesh. First, element type. Select the whole region. Bin. And here we have shear force and cubic formation. So I want to explain here what this shear flexible and cubic formation mean. So shear flexible means that if your beam is kind of thick, and for the shear stress is distributed in a way like this, right? This is what you learn from the mechanics materials. And this shear stress, because it's thick, so this shear stress cannot be ignored. So when you bend, this shear stress will create a what definition of shear stress? The change of angle, right? So this has shear stress here. But if you have very thin beam, this shear stress is very small. It's very small and it can be ignored. Same here. And we can assume that here shear stress is 0. And so when it bends, this angle doesn't change. So this is the Timoshenko beam theory, and this is Euler-Blue beam theory. And so it's corresponding to the shear flexible and cubic formation here. And in our all the problem in this semester, we only consider this situation. Shear stress not considered. Shear stress always equal to 0. This angle doesn't change. The definition of shear stress is a angle change here, right? So, and also this cubic formation is the same as what I just said. We use a cubic polynomial to do the interpolation. So remember, always choose this as cubic formation, because if you don't change it, by default it's shear flexible. You will have some error in your result. And now let's do the seed. As I said, for the beam problem, you can use as many elements as you want, and it's determined by your loading condition and the accuracy, the requirement of accuracy. So now I will just try to this default setting as 0.2. So we have 5 elements here, 10 elements here, and 5 elements here. And now last step, mesh instance. Yes. So you can hear 20 elements have been generated. And if you want to see the node label and element label, can see node label from 1, 2, 3, 4 here, and also in between. And this yellow is element label. We probably need to remember, I will write it here. So later we'll have the result of the bending moment along this beam. And Abaqus will plot this bending moment along this load label. So it's from 2, and then you see here 9, 10, 11, so from 9 to 17. And the last node is 3. Because later when we plot this bending moment along this line, we need to give the information of this node label. Now let's I think everything's done. We can create a job.
Didn't you define 4 nodes already, and then you
Yeah.
define the distance between each node? What happens in the case where it's not an even split between the distance between each node and your beam or truss or whatever your figure is itself?
I'm not quite understanding your question. Could you please?
Say if your element distance doesn't split evenly into, say, the length of your truss, what is that basically?
You can see it differently, one by one, different define it in the way you want. I just like use 0.2 for the whole model, but if you want like sitting 1 element here and 10 elements here and 2 elements here, you sit one by one separately. This is the result. So, deformed geometry. Makes sense, right? And this is from its stress. Let's change the viewport annotation option. Make legend, change the legend. Is it better?
Yeah.
Okay. So let's see S11 sigma xx. This is the stress sigma xx, and what we can do is that we use the show tick marks for line elements. Apply, and then we put it on the original geometry. Can see this. So using this one, you can know the like approximate value of this sigma xx. So you can see here the sigma xx linear change on this beam, sigma xx linear change on this beam, and here is changing quadratically. And if you compare this tick marks with this legend, you can know the result, the approximate results here. And also SM, bending moment, same here. And if you want to do a plot, we can also use this one. This is another way to check the result. So go to Tools, use Path, create a path. As I said, if I want to know the bending moment or sigma axis along this truss, I can create a node list. And you can see here, I need to give the node label information. That's why I just write down here from this node to this node is 2. And then from 9 to 17. And the last node is 3. So it will create a node list along this beam. It has example here, so if it's a single node, you can just type as single node. If it's like 5 and then 10, it means that from 5 to 10, and the increment is 1. If you put a 2 here, it means that increment is 2. So it's the same thing as in MATLAB. You can also use add before, add after. It's the same thing. So if you use add before, add after, you can try later in after class. You just click each node on it one by one. It's the same way. It's the same thing. So I will just, since I already have this node label, I will input here, and we'll see. After we create the path, now we can use XY data tool, XY data, and create. And use the path I just created, the path 1, and x distance, true distance is the same. X distance means distance in x direction, distance in y direction, and distance in z direction. And normalized distance is that no matter what length these distances, I always use 1 as a, so it's like normalize this distance. True distance is the true size. Field output, we can select so this is x value. What is the y axis you want to use? So if I want to plot the bending moment, we can select the section moments at integration points, apply, and plot. Wait a second. How about I use x distance? Okay. So you can see that the lowest bending moment is here, and it's decrease, and then increase at this node. And also, you can change this to, if you want to know sigma xx stress and S11 plot. So this is how sigma xx change. And so these are two different plots you can use in your report. And one thing I want to emphasize here is that, let me remove this marker first. There is a bottom and also upper. So what does bottom or upper mean? For S11.
Stress at the bottom face of the beam.
Yeah. Bottom surface or top surface. So for truss problem, the sigma axis, no matter it's bottom surface or upper surface, the sigma axis is always the same, right? But for beam problem, if you bend it, and then, for example, if I want to bend it this way, and then like this, right? So the sigma xx linear change through the cross-section direction area. So the sigma xx on the bottom surface and upper surface is different. So you can change this you can change this if you want to see the result at the upper surface. So result and section point, you can change this to top. Apply. You can see top. This is so you must be clear that the plot is the plot from the upper surface or from the bottom surface, top surface or bottom surface. And another question is that I already said at the beginning, for different loading condition, sometimes one element is enough. Sometimes we can only do the approximation because the Abaqus for beam problem only can do the cubic polynomial. So for this 3-beam problem, what is the best way to do the seating? It's like always more element, the better, or for some beams, you can just use one element. For some beam, we need to use more elements to estimate, to do the approximation. So just now I used 5 elements here, and I think 10 elements here and 5 elements here. Now we can change the mesh and see. I delete this mesh. And I do the seating again. So if I change this to 1, as trust problem, I change this to one element on one bin. Let's see what the result will look like. So you can see one element here and one element here and one element here. So mesh instance. 3 elements have been generated. Now let's run the job again. So what's the problem here? What's the problem here? Yeah. For which element?
The top one.
Yeah. So if I change the mesh to one element here, one element here, one element here, actually these two is the same, right? Because for these two being, it's only subject to concentrated force. And for concentrated force, bin element type in Abaqus can give you accurate results. So one element is good enough. But for this bin, because it has concentrated force and distributed force at the same time, and Abaqus can only do the approximation. So if you use just one element, it can only, like, the result is not accurate. So if we go to the tools and path, same load list, continue. And I show you how to do this one. I click this one and click this one. This is another way to create a path. So if I don't know the node label, done. So 2, 3 here. And then I use tools, XY data, create, and path. Yeah, I just created. Okay, dismiss. Path 2. Let's see the S11 plot. Now you can see the S11 linear change from here to here. So the true result should be start from here and decrease, 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 and then increase. So this should be the minimum result, right, around here. But if you only use one element, you will miss this minimum result and show you like the result will be not accurate. That's why you need to use your background knowledge to determine how many elements is the best for your problem. Any question? So if no question, that's all for today. Thank you for coming.